Recording is rolling. This is fifth period AP Physics. This is Wednesday, September 29. And we're looking at this friction lab that you guys did yesterday. So I'm just going to give you guys a debrief. So this friction lab was in two parts. Now, each of the parts you were trying to figure out was the coefficient of friction, but from really different points of view. The first part, you guys remember, you took some lab weights, which remember I wrapped in paper to control for materials because coefficient of friction is a material property. So paper against paper, for example. And you could drag it with a spring scale, read that force, lift it, read that force. And what you guys had in mind was this free body diagram where if you were pulling with a spring scale, the correct way to pull it was two conditions, horizontally and at constant velocity. So horizontally, so that the only two vertical forces would be exactly balancing. So this is equal to this. And at constant velocity, so that, what's the importance of constant velocity? Yeah, so these two forces are equal. So that you can get friction by reading the spring scale, right? That's what constant velocity is about, because that's an example of equilibrium. Right? And then this is the definition of coefficient of friction. It's the ratio of these two forces, right? This over this. Okay? But if this thing's in equilibrium, isn't that also equivalent to F pull over weight? Sure would be, wouldn't it? Which is where I was having you guys go with this graph, F pull versus weight. I'll show you guys the ideal textbook answer to that. It should have looked like that right there. Right? Now, if your data said otherwise, then, well, your data is the absolute truth of the universe, but this is the ideal textbook answer. So pulling force versus weight should have been a linear relationship. Like if you had double the weight, it should have been double the pulling force. Triple the weight, triple the pulling force. And the slope of that line should represent coefficient of friction, which makes sense also if you think about it from the definition point of view. Actually, you could rearrange this and get AP's version of friction. Isn't friction force equal to coefficient of friction multiplied by the normal force? Which is exactly what this says. Right? That's the equation of this line. So when I said F pull equals, which you guys told me also represents the friction force, hey, doesn't that look like y equals mx kind of deal? Doesn't this look like y equals mx? So the pulling force should have been the coefficient of friction multiplied by the weight. That's it. Of course, you guys remember the title of the graph tells you what goes on which axis. So pulling force versus weight, pulling force versus weight, they're all in newtons. Right? What's the units that go along with this slope? What's the unit? Yeah, you're on to it. Yeah. So Newton per Newton, it's unitless, right? It just cancels out. Okay. And then what does mu represent? So I want to see what you guys came up with that, but you could have said the slope of the line. That would be true. You could have said coefficient of friction. That's also true. So see what you guys come up with that. Right, now the second half of the lab was a different point of view. What I had you guys do was to put a various lab weights. So again, you're working with various lab weights for each part on a surface, and then like an incline, and then lift that surface until it breaks the friction and starts sliding down. Okay? Or actually, the way you just phrased that is one point of view, but you could have done something a little differently and solved for something else. But talk about that in a minute. So measure the angle that it breaks that friction, and then I told you guys to take the tangent of that angle, but I didn't tell you guys why. But I think some of you guys figured it out. Who figured out what the tangent of the angle is all about? Yeah, looks like about a third of the class. Okay, so awesome if you did. I know some of you guys did because I walked around and saw you guys figured it out. Then how do you guys graph tan theta versus weight? So before I show you guys that graph, what the heck is tan theta about? Okay, well, let's look at a free body diagram with this from the side. So what angle are we even talking about? We're talking about the angle with respect to the horizontal, so you wouldn't want to specify that. I did leave off some critical details like pull horizontally at a constant velocity, or theta with respect to the horizontal. Okay? But that's what that would be. Now, this free body diagram you guys are looking at is showing a case of equilibrium. And if that's true, that means all the forces balance. Now, there are only three forces. You guys see three forces? If AP wants you to draw this, you just draw those three right there. But what I commonly do is split the weight into these components because that makes it very convenient to analyze. Because then now I know the normal force is exactly equivalent to the cosine component of the weight. And, look at this. Wouldn't the friction force also be balanced with the sine component of the weight? Okay. Now, is that universally true? Is the friction force always equal to mg sine theta? No, not universally. It's only true in the case of equilibrium. And also notice that there's no like extra strings. It's not part of a larger applet system, anything like that, which would also throw this off, right? You guys have this poster and all the other posters on. I put them in a file on Google Classroom. You can go find that. Okay. Oh, yeah, you have a.
What if you changed like the coefficient of friction between the materials?
That's a good point too. So it's asking, what if you change the materials? So remember that coefficient of friction is a material property. That's why I was like wrapping this in paper. So I have paper against paper. So I was controlling for the materials. Now, if you went with like the Bear Lab weights, or you went with ones that were painted in black paint, those would be different materials, and so you would probably get slightly different versions for coefficient of friction. Okay, so that's one thing that if you're really scientific about it, you want to control for. Right? Okay. All right. So back here, I see a sine theta. I see cosine theta. What the heck is up with a tan theta? Oh, equilibrium. Now here's where too I want to mention that you could have actually been solving for one or two slightly different angles. So if you found the angle where it first breaks the friction, then that would be a little bit steeper than if you found the angle that the block moves down the incline at constant velocity. Right? That would have been a little bit shallower angle. That first one I mentioned, where it initially breaks the friction, you would have been ultimately solving for which coefficient, static or kinetic friction. Static, where it initially breaks the friction. The one where it's moved sliding down at constant velocity, isn't that a kinetic friction type of case? Right? Is that true? Which would have been at a shallower angle. You would have gotten a coefficient of friction that was a little bit less. But the free body diagrams would have looked pretty much identical, wouldn't they? If you did not know if this was static or kinetic friction, it would be ambiguous because those would both represent equilibrium. Right? Now, how's this all come together? Well, you guys remember, reveal this way, that coefficient of friction is defined as the ratio of friction force to normal force. Right? Actually, it's really equals always for kinetic friction. For static friction, you could say if it's just at the breaking point, which could have been what you were looking for, right? But look at this free body diagram. Now, you guys know that normal force could be equivalent to mg cosine theta, so I could make that substitution. That's what I'm going to substitute there. But for equilibrium, mg sine theta is also equivalent to the friction force, so could you also make that substitution? You can make both of the substitutions, couldn't you? Is that right? And if you do that, then the coefficient of friction is defined as mg sine theta divided by mg cosine theta. If you didn't see where the tan theta has come from before, I bet you see it now. So, hey, the mass cancels out, which is a really common thing to happen in this class. You guys have seen that many times before. Also, the gravity field cancels out. Which means that if you were to take this whole experiment to Mars, which has about a third of Earth's gravity, then would anything change about the experiment at all? No, it would work out exactly the same because the magnitude of the gravity field does not matter. It matters that you have gravity, but once you have gravity, it doesn't matter after that. What is sine theta divided by cosine theta? Tan theta. It is. So tan theta actually represents the coefficient of friction. And depending on exactly how you set it up, it could be static or kinetic. I'm going to guess that most of you guys probably did the static case where it initially broke the friction. And if you did do that, if you did the static point of view, then I bet that your coefficient of friction that you got on the second half lab is a little bit more than the first half. For example, you might get like 0.4 versus 0.3, something like that. I bet that's how it played out for most of you guys, and you can check your numbers and see if it did. Okay? So come to think of it, the first way you did coefficient of friction might be like using scales and spring scales, but do you even need a spring scale at all to measure coefficient of friction using this method? No, you only need what tool? Protractor. This right here. You can actually get coefficient of friction without using a scale at all. You can just use a protractor. Okay? It's a way to do it. That's been an AP question in the past too. So like experimental design. Okay? So I wonder what this graph is going to look like. Well, if for various weights, if they all break at about the same angle, because remember, mass and the weight canceled out, right? So they should all break at about the same angle. Then shouldn't tangent of that angle also be like the same ratio over and over? So maybe your breaking angle was like, for example, like 11 degrees, 12, 10, 14, 13, but it should all been kind of in the ballpark of the same, pretty much the same angle. Okay? So the tangent of that angle would also be the same, which means that the graph of tan theta as a function of weight should have been constant, right? In that constant value, of course, I just showed you guys the proof, represents the coefficient of friction. Yeah. You guys good so far? Right. So that's a general debrief, but I'm going to give you guys a scoring rubric. So break out those color, you guys see those colored pencils on your desk? Colored pencils? Right. Now, I said just do one of the write-ups, so either the left half or the right half. So whichever one you do is fine. I've got both scoring rubrics here, so just follow along with whichever one is applicable to you. And score out of 7, I came up with a 7-point rubric, 7 points. Right, so either way, you're trying to find coefficient of friction. The left side is specifically kinetic friction, and the right side, I bet most of you guys probably found static coefficient of static friction, but you could have done the other way. Right. Measuring tools. So for the left, for the first setup, have a spring scale. If you said something like I guess you could have used other tools like balance beam or something, but have spring scale for your measuring tool, that's worth a point. Right? If you did the incline method, then definitely you had to have mentioned the protractor. If you also mention things like a balance or something like that, then that's okay too, but definitely have to mention the protractor, so a point for that. Actually, that's the only tool you really needed. Right, data gathering procedure. Right, so the slide with the spring scale method, choose several lab weights, different masses, cover those lab weights in paper, for example, so they have the same surfaces, so that's controlled. Also find a horizontal surface. Okay, so 1 point for describing the lab setup. Hang the lab weight using a spring scale, record that weight in newtons, and then using the spring scale, pull the weight horizontally across the horizontal surface at constant velocity. Notice I mentioned those important details. Pull horizontally at constant velocity, those are both important. Record the pulling force in newtons, so 1 point for application of the spring scale. Then repeat the previous step 2 more times and record and find the average pulling force. 1 point for multiple trials. If you pay real close attention, maybe that was an easy step to miss because the table that I set up for you guys does not explicitly make use of that. But you guys know for your AP write-up in May, this is going to be worth a point somewhere, right? Okay. So multiple trials, that's worth a point. And then finally, repeat the previous steps using the other lab weights. Okay. So that's how you're going to gather the data. Now, if you did the incline method, this is the other method, the second lab, capital F. Choose several lab weights of different masses, cover those lab weights in paper, for example, so they have all the same surfaces, control for the materials. Also find a flat, tiltable surface. 1 point for describing the lab setup. Place the lab weight on the tiltable surface. Use the protractor to determine the horizontal plane, and then tilt the desk until the lab weight breaks the friction and begins sliding down the surface. Record that angle in degrees, so 1 point for use of the protractor. Now, the way I described this is geared specifically to find the coefficient of static friction. You could have done something a little bit differently to find the other one, and that's okay too. Okay. Step 3, repeat the previous step 2 more times and record the average pulling force, so 1 step to say multiple trials. And then finally, repeat the previous few steps for each of the lab weights. Okay. So, well, I guess this should have been 2 through 3, but whatever. Okay. Guys good? Right, so that's just gathering the raw data. Okay. Now on to data analysis. Right, so the first half of the lab with the spring scales, graph pulling force versus hanging force, which I set up for you guys right here. Pulling force versus weight, same idea. Alternatively, graph friction force versus normal force, since those are identical values. So 1 point if you mentioned putting into a graph, that's one thing that AP likes is that you put things in the graphs and that you know properties of graphs. The coefficient of friction is equal to the slope of that line. So 1 point for property of the graph that determines the answer, which of course would be slope in this case. Okay.
Is it fine if we said to just take the 2 variables and divide them like paper? Do we need to do this?
Yeah, I think if you said, yeah, just divide them and then like take the average of those ratios, that would work too. I would give you credit for that. Having seen enough of these rubrics, if you can incorporate a graph, then sometimes AP raises it like this, so it depends on how strict the AP grader is, but I would give you credit for that. Okay. And then let's just do the conclusion. Conclusion, coefficient of friction, coefficient of kinetic friction, use of K, between paper and paper is some number, maybe like 0.3 or something. Okay? So 1 point for a conclusion that answers the question. Right, now, if you were doing the incline method, let's look at your data analysis. So find tan data for each of the angles. So 1 point for describing method that will ultimately lead to the answer. And then the coefficient of static friction is equal to the average of those tan data. So 1 point for property that determines the answer. Alternatively, find tan data for each of the angles, graph tan data versus lab mass, and then the coefficient of friction is equal to the horizontal value of that graph. So the graph is maybe kind of overkill, but I did put the graph here, and you can actually use that method to do it. So whether you use the graph or not, taking tan data, and actually really what I should have included in that write-up is this whole proof that I just showed you. Because normally what AP does is they like a point for this, and a point for this, and a point for this. That's usually how they award points. So really ideally you should have this proof as part of your data analysis if you did the incline method. Okay. And then, of course, conclusion, coefficient of static friction between the surfaces is something, maybe like 0.4 or something, right? So 1 point for a conclusion that answers the question being, what is the coefficient of friction? Okay. Any questions on any of that? All right, so hang on to that page until the end of class. When you guys are walking out today, I'll have you guys turn that into the grade tray. But I'm also gonna have you guys turn in, there is clipped to the front of your desk and FRQ. Okay.